Welcome back. This lecture is a continuation of my earlier lecture, and the specific objectives of this particular lecture are to introduce solar radiation through fenestration, define solar heat gain factor and shading coefficient, discuss effects of external shading, introduce ventilation and infiltration, and discuss estimation of heating and cooling loads due to ventilation and infiltration. So, at the end of the lecture you should be able to estimate heat transmitted into a building due to solar radiation through fenestration using values of solar heat gain factor and shading coefficient from tables, calculate dimensions of the overhangs for external shading, explain the importance of ventilation, and estimate heating and cooling loads due to ventilation and infiltration. Before that, let me just work out an example on calculation of solar radiation on a south facing wall. The example is like this: you have to calculate the total solar radiation incident on a south facing vertical surface at solar noon on June 21st and December 21st using the data given below. The latitude angle is given to be 23 degrees centigrade and the hour angle is 0 degrees because it is at solar noon. Okay, this is not given, but you have to infer this from the given information. And the declination is plus 23.5 degrees on June 21st and minus 23.5 degrees on December 21st. And the tilt angle here is 90 degrees because it is a vertical surface. And the wall azimuth angle zeta is 0 degrees centigrade because the wall is south facing. And finally, it is given that the reflectivity of the ground is 0.6. So, this is the information given. And based on this we will have to calculate the total solar radiation. Okay, so here a stepwise procedure is shown. First what we do is we find out the altitude angle beta. Since we are doing the calculations at solar noon, the beta is nothing but beta max, that is given by pi by 2 minus absolute value of L minus D, where L is the latitude and D is the declination. So, you find that the altitude angle works out to be 89.53 degrees. First I am doing the calculation for June 21st. Okay, so here I take the declination as 23.5 degrees. Next, at solar noon we have to calculate what is the solar azimuth angle. Since we are making the calculations at solar noon, the solar azimuth angle is either 180 degrees or 0 degrees. It is 0 degrees if latitude is less than declination. So, you have to take solar azimuth angle to be 0 degrees in this case. Okay. And next we have to calculate what is wall solar azimuth angle alpha. The wall solar azimuth angle alpha is given by 180 minus gamma plus zeta, and here you find that gamma is 0 and zeta is also 0. So, you find that the value of alpha is 180 degrees for this particular case. Okay, once you know the value of alpha and the value of beta, we can calculate the incidence angle. Since this is a vertical wall, the incidence angle is given by theta vertical is cos inverse cos beta into cos alpha. Beta is 89.53 degrees and alpha is 180 degrees. So, from this you find that the incidence angle is 89.53 degrees. Once you know the incident angle, we can calculate what is the direct radiation on the surface. The direct radiation is given by IDN cos theta. So, first let us find out IDN. From the ASHRAE model, IDN is given by A multiplied by exponential within bracket minus B by sin beta, where beta is altitude angle, that is 89.53 degrees, and A is 1080 for summer. So, you take the value of A as 1080, and B, which is called as the extinction coefficient, it takes a value of 0.21 for summer. These aspects I have discussed in the last lecture. Okay. So, you take these values of 1080 for A and 0.21 for B and substitute the value of beta, you find that the direct normal radiation is 875.4 watt per meter square. So, we have to find out what is the direct radiation on the vertical surface. So, that you have to find out by multiplying this with cos theta, where theta is the angle of incident. Okay, that is the 89.53 degrees. So, if you find that, you will find that IDN cos theta works out to be 7.18 watt per meter square. Okay. Next, we have to find out the diffuse radiation. Diffuse radiation, for that we have to find out the view factor. View factor is given by 1 plus cos epsilon by 2, and this is 90 degrees. So, you find that view factor is 0.5. Okay, this is for the diffuse radiation. Once you know the view factor, diffuse radiation given by, again based on the ASHRAE model, ID is equal to C into I subscript dn into F subscript WS, where C takes a value of 0.135 for summer. Since I am making the calculations for June, I take a value of 0.135, and IDN works out to be 875.4 as shown in the last slide, and FWS is 0.5. So, if you substitute all these values, you find that the diffuse radiation is 59.1 watt per meter square. Next, we have to find out the reflected radiation. Reflected radiation also has a view factor between the ground and the wall. So, first let us find the view factor between the ground and the wall, that is F subscript WZ, this one, that is given by 1 minus cos epsilon by 2. So, this works out to be 0.5. Then based on the Ashtray model, the reflected radiation from the ground is equal to IDN plus I diffuse multiplied by rho z into FWZ, where rho z is the reflectivity of the ground, which is given as 0.6, and FWZ is 0.5. So, if you substitute the value of IDN and I diffuse, you find that the reflected radiation works out to be 280.36 watt per meter square. So, the total incident radiation is nothing but sum total of direct radiation contribution, diffuse radiation and reflected radiation. So, the direct radiation, total radiation works out to be 346.64 watt per meter square. Okay, so, this is a fairly straightforward procedure. This is for a vertical wall. If the surface is inclined, then you have to use the tilt angle, and if it is facing any other direction other than south, then you have to use proper surface azimuth angle, okay, as explained in the last lecture. In the same manner, you can calculate all these parameters for December 21st. Okay, for December 21st, the declination angle will be minus 23.5 degrees. Okay, so now let me show a table where the solar radiation results for June 21st and December 21st are given. So, this table shows the comparison between June 21st and December 21st. June 21st, you find that the incidence angle is 89.53, whereas for December 21st it is 43.53. The direct radiation IDN is 875.4 watt per meter square in case of June 21st, and it is 1003.75 in case of December. Similarly, the contribution of direct radiation is nothing but IDN cos theta is 7.18 watt per meter square for June and 727.7 watt per meter square for December. Okay, and the diffuse radiation is 59.1 and 29.1, and reflected radiation is 280.36 and 39.9 in case of December. So, the total incident radiation on the vertical surface is 346.64 watt per meter square on June 21st and 1066.7 watt per meter square on December 21st. Okay. This example actually gives us some useful information. That information is that this is a south facing wall. You observe here that for south facing wall, if you get the total radiation incident on the wall is 346.64 watt per meter square in summer, whereas it is almost 1100 watt per meter square in winter. Okay, and here for summer, this value is coming because of the reflected radiation, because we have taken 0.6 as the reflectivity of the ground. If the ground is not so reflective, you find that the total incident radiation on the vertical surface on June will be very small, whereas it is very high on the on December 21st, or that is in winter. Okay, so this tells us this gives us an important information, that is that for south facing walls, the solar radiation incident on a vertical surface is much less in June, whereas it is much higher in winter. Okay. So, since we want to reduce the load, heat load on the building during summer, and we want to maximize the heat transfer to the building during winter, it is always beneficial to keep windows, doors, etc. on south side. Okay, so that the radiation part will be small in summer and it will be large in winter. So, your cooling capacity requirement will be small and the heating capacity requirement also will be small. Okay, so this is a principle generally used in passive cooling and heating techniques. Okay, use the south wall properly, and of course these results hold good for northern hemisphere. Okay, because the latitude is 23 degree north. The results will be different if we are talking about southern hemisphere. Okay. And so far this Ashtray model, in fact if you remember, I have mentioned in the last class that this model assumes that the sky is cloudless. Okay, but if the sky is cloudy, sometimes what is done is a clearness index value is used to calculate the incident direct solar radiation. Okay, the clearness index value is 1 if the sky is clear, and it will be less than 1 if the sky is cloudy. Okay. And the clearness index value for different regions during different seasons are available. Okay. So, from that data you can calculate what is the radiation during a cloudy day. Okay. Now, next let us look at solar radiation through fenestration. First of all, what is fenestration? Fenestration refers to any glazed apertures in a building such as glass doors, windows, skylights, etc. That means it refers to all those transparent surfaces such as doors, windows, skylights, etc. Okay. All these are called as fenestration. We need fenestration, all buildings have fenestration. Why do we need fenestration? It is required because it provides daylight, heat and outside air, and fenestration also provides visual communication to the outside world. It also improves aesthetics, and finally it provides an escape route in case of fires in low rise buildings. Because of all these factors, almost all buildings will have some amount of fenestration. That means you will have some amount of glass windows or glass doors, etc. Okay, because of the 4 reasons mentioned here. Now let us see what is the effect of this on the cooling and heating loads. Heat transfer due to solar radiation through transparent surfaces is distinctly different from heat transfer through opaque surfaces. This is one important thing to note. Okay. What is the difference? Radiation incident on an opaque surface, for example a wall or a roof, is partly absorbed and the remaining is reflected back. Because it is opaque surface, so its transmittivity is 0. So whatever radiation is incident, either it is absorbed or it is reflected. That means it is partly absorbed and partly reflected. And out of the absorbed part, only a fraction of it is transferred into the building. This aspect we will discuss in the next lecture. So ultimately, whenever radiation is incident on an opaque building, some of it is absorbed and some of it is reflected back, and out of the absorbed portion only a part is finally transferred to the building. That means only a part of the radiation incident on an opaque surface finally becomes a load on the building. Okay. This is as far as the opaque surface is concerned. Now let us look at a transparent surface. For a transparent surface, a major part of the radiation incident on a transparent surface is directly transmitted into the building, while the rest is absorbed and reflected back. We know this from our basic physics that all transparent surfaces have high transmittivity. Okay, so whenever radiation is incident on the surface, most of it is transmitted through the surface, right? Transmitted through the glass, and only a small part of it is absorbed and a small part of it is reflected back. So this is a major difference between the transparent surface and opaque surface, and this has a huge effect on the heating and cooling loads. Okay. First let us look at a reference surface and see what happens to the radiation. Okay. This is a distribution of solar radiation on a clear plate glass. Okay. For a clear plate glass, clear plate glass has these optical properties. It has a transmittivity of 0.8, it has an absorptivity of 0.12, it has a reflectivity of 0.08. Okay. So these are the values for the solar radiation. For solar radiation, these are the values. Now since it has a transmittivity of 0.8, if 100% of solar radiation is incident on this window, okay, which is nothing but your window made of clear plate glass, 80% of it is directly transmitted to the indoors, okay, because it has a transmittivity of 0.8, right, and 12% of it is absorbed by the glass, while 8% of it is reflected back. Okay, this is based on the optical properties of the clear glass. Now of the 12% absorbed, what happens to this 12% of the radiation absorbed by the glass? This will increase the temperature of the glass. That means glass temperature increases due to absorption, okay, absorption of radiation, right. So once the glass temperature increases, it rejects some heat by convection to the outside, and some part of it is rejected to the indoors. Okay. So for example, typical values are this particular glass will reject about 8% to the outside and about 4% to the indoors. So finally you see that out of the 100% solar radiation incident on the surface, 80% plus 4%, that is 84% is directly transmitted to the building or to the indoors, while 16% is transmitted to the outside. Okay. This is for a clear plate glass, and these values will be different for different types of glasses. Okay. Now, what is the importance of fenestration on glazed surfaces? Why do we have to consider this seriously? Fenestration or glazed surfaces contribute a major part of cooling load of a building. Okay. So, the energy transfer due to fenestration depends on the characteristics of the surface and its orientation, weather and solar radiation conditions. So, careful design of fenestration can reduce the building energy consumption considerably. Okay, so if you design it properly, then fenestration can help you in reducing the initial and running costs. But if you don't design it properly, then you will have to pay both in terms of initial and running costs. For example, if you design the fenestration properly, that means if you put the glass, windows, doors, etc. Properly on proper direction and with a proper orientation, you will find that the radiation transmitted to the building during summer can be reduced very much, whereas it can be increased very much in winter. As a result, the cooling load on the building can be reduced during summer and the heating load on the building can be reduced in winter. Okay, so the required cooling and heating capacities will be less, so your initial and running costs will be less. Okay, so if you are using the fenestration properly. Okay. Instead of that, if you are putting glass left and right just to increase the aesthetics or anything, you will find that both heating as well as cooling loads will increase. Okay, so ultimately you will have to pay for this in terms of initial and running costs. Okay, so that's why it is very important to understand the importance of fenestration and the issues involved in the design of fenestration for buildings. Now, let us look at a simple model for calculating solar radiation passing through a transparent surface. Okay. So, this model is based on these assumptions. The assumptions are like this. So, this is valid under the assumption that the transmittivity, that is the tau value, and absorptivity, that is alpha value of the fenestration is same for both direct as well as diffuse radiation. This is an important point to be remembered. In actual case, you find that the transmittivity and absorptivity of the glass will be different for direct radiation and diffuse radiation. Okay, the values will be different, and the transmittivity and absorptivity values of direct radiation, okay, it depends strongly on the angle of incidence, right. So, this is again a very important point to be remembered. The transmittivity and absorptivity of the glass for direct radiation is not a constant. Okay, so it is a function of the angle of incidence, and as we have seen, the angle of incidence itself varies. It varies with the latitude, it varies with our angle, it varies with the declination and with the orientation, etc. Right. So, based on this, the transmittivity and absorptivity of the glass also varies, whereas the transmittivity and absorptivity of the diffuse radiation remains more or less constant. Okay. However, the model that I am going to present, which is taken actually from ASHRAE handbooks, it is based on the assumption that the transmittivity and absorptivity values are same, are constant, and they are same for both direct radiation as well as diffuse radiation. However, this assumption is justified because normally we do the calculations for the peak load conditions. Okay, and at peak load conditions you find that the contribution of direct radiation is much larger compared to the diffuse radiation. I am sorry. So, direct radiation is much larger than the diffuse radiation. So, if you are assuming that the tau values and alpha values are same for both, you will not be making a huge error. Okay, and besides it simplifies the procedure. However, it is not necessary that you have to assume them to be same. Okay, with a little bit of extension, you can take different values of tau and alpha for diffuse radiation and direct radiation and do the calculation separately. Okay. So, under this assumption, you can write the solar radiation transmitted to the building Q subscript Sg, okay, is equal to A multiplied by within brackets tau into I subscript T plus N multiplied by alpha multiplied by I subscript T. Here as I said, QSG, okay, is the radiation transmitted to the building and the units are watts in SI units, okay, and A is the area of the surface exposed to radiation in meter square. IT is the total radiation incident on the surface. So, this includes both direct plus diffuse. Okay. Of course, you can also include reflected radiation. Normally reflected radiation will be a small part. So this includes the total radiation incident on the surface, and tau is, as you know, is the transmittivity of the glass, alpha is the absorptivity of the glass. And what is n? N is a new parameter, and this is the fraction of absorbed radiation transferred to the indoors by conduction and convection. In fact, I was mentioning that when the glass absorbs radiation, its temperature increases. So because of the temperature difference between the glass and the surroundings, there will be heat transfer due to convection. Okay, so this factor n takes into account this heat transfer. That means the heat transfer due to convection because of the temperature difference between the glass and the surrounding air. Okay, and it can be very easily shown that at steady state the value of n is given by u divided by h naught, where u is the overall heat transfer coefficient, okay, and h naught is the external heat transfer coefficient. So u is the overall heat transfer coefficient for a flat glass 1 by u. You know that the expression 1 by u is 1 by hi plus 1 by h naught plus delta x by k wall. Okay, this is the resistance of the wall, this is the convective resistance on the outside, this is the convective resistance of the inside. Okay, so you can calculate overall heat transfer coefficient, and h naught is the external heat transfer coefficient. Okay, so if you know the overall heat transfer coefficient, external heat transfer coefficient, properties of the glass, and if you can estimate the total radiation incident on the surface as we have shown in the example, last example, you can calculate what is the solar energy transmitted to the building. Okay, through fenestration. Now what we can do is from the last expression we can write QSG like this. Okay, A and take out A, and you can also take out IT. So you can write QSG is A into within brackets IT multiplied by within bracket tau plus alpha u by h naught. As I said, tau is the transmittivity, alpha is the absorptivity, u by h naught is your fraction n. Okay. Now what is done is a single sheet clear window glass. Okay, a single sheet clear window glass is taken as a reference, and a factor called solar heat gain factor or SHGF is defined as follows. Okay, so taking the single sheet clear window glass as reference, we define a solar heat gain factor as this. This is nothing but total radiation incident on the surface multiplied by within brackets tau plus alpha u by h naught. Okay, and the subscript stands for, subscript SS stands for single sheet clear window glass. That means it is for the reference glass. Okay, you will see immediately what is the advantage of defining this. The advantage is that the maximum solar heat gain factor values for different latitudes, months and orientations have been found and tabulated. For example, ASHRAE handbooks gives the maximum solar heat gain factors for different latitudes, months and orientations, etc. So once you know the solar heat gain factor, maximum solar heat gain factor from the table for a given latitude, for a given orientation, for a given day, then you can calculate what is the energy transmitted into the building if the glass is made of reference glass, because the energy transmitted is nothing but area multiplied by SHGF, right. So let me show you a typical table adopted from ASHRAE handbooks. Okay, so this is this table gives maximum solar heat gain factor for sunlit glass, okay, located at 32 degrees north latitude, and the units here are watt per meter square. Okay, for example, for month December, okay, orientation of the surface, if the window is facing north or window is shaded, then you find that the maximum solar heat gain factor is 69 watt per meter square in December, it is 75 watt per meter square during January and November, it is 85 during February and October, and 100 during March and September, like that. Similarly for northeast and northwest, that means the window is facing northeast or northwest direction, then during December this is the value, during January and November this is the value, February this is the value, like that. Okay, like that it gives the solar heat gain factor, maximum solar heat gain factor for all orientations, for different orientations, okay, the 8 orientations, and also for horizontal orientation. For all these we are assuming that the glass is vertical, okay, that means the tilt angle is 90 degrees. Okay, so that means on a vertical wall, right, and this data is valid for 32 degrees north latitude. ASHRAE handbook gives this similar data for other latitude also, for example 24 degrees, 40 degrees, like that, right. So from this table you can calculate what is the maximum solar heat gain factor. For example, I would like to find out during the month of July, I want to find out what is the solar heat gain factor through a south facing window, okay, that value is given by 230, right. During a east or west facing window it is 685, like that we can find out the SHGF maximum. One interesting thing you can observe here is the benefit of putting the window on the south side. As I was mentioning in the last example, you can see that for south side windows, okay, the maximum solar heat gain factor, that means radiation transmitted into the building because of solar radiation through the glass, is very small during summer, whereas it is large during winter. Okay. What we want is, we would like to heat the buildings in winter using solar radiation, okay, and we do not want any solar radiation into the building during summer, right, because that way you can keep the building cooler during summer and you can keep the building warmer during the winter, so using the solar radiation, right. So this is very beneficial, and this is very beneficial only when you put the windows on the south side, because you see that for the south side there is practically not much radiation during summer, whereas there is a lot of radiation during winter, okay. Whereas for other directions like east west, you find that it is almost same during throughout the year. So you should not put, you look at the table for east west, the solar radiation is almost constant throughout the year, okay, maybe some 20-30% variation is there. That means you should never keep windows on east or west direction, because on east or west directions during summer you will receive lot of radiation. Of course, during winter also you receive radiation, but not as much as you receive if you put the window on the south side, okay. So this kind of handbook data are available in the handbooks. Now this data is for a standard reference glass. How about other glasses? For fenestrations other than the reference SS glass, a shading coefficient is defined, okay. This shading coefficient is defined such that the heat transfer due to solar radiation is given by QSG that is equal to area A, okay, multiplied by SHGF maximum of the standard glass multiplied by the shading coefficient. So finally you find that shading coefficient is nothing but the heat transmitted through the actual glass divided by the heat transmitted through a standard glass, okay. That is how the shading coefficient is defined, and the shading coefficient depends upon the type of the glass and also on the type of the internal shading devices, okay. You can use a wide variety of internal shading devices, as you know very well. If you want to shade the window from radiation, you can use curtains, you can use Venetian blinds, rollers, like that, okay. So the shading coefficient depends upon what kind of internal shading device you are using, and it also depends upon what kind of glass you are using, whether it is a double glass or a single glass, etc. Okay. And typical values of shading coefficient for different types of glass with different types of internal shading devices have been measured and are tabulated, for example in ASHRAE handbooks, okay. So let me show a typical table. Again this is taken from ASHRAE handbooks. This table gives shading coefficient for different types of glass and internal shading. For example, for a type of glass, for a single glass, okay, single sheet regular glass, this is the standard glass. If it has a thickness of 3 mm and if it does not have no internal shading, the shading coefficient is 1. The shading coefficient is 1 because this glass is taken as the reference, okay. So for this glass the Q is simply A into SHGF maximum that you get from the table, right. However, if you are using internal shading device, for example if you are using Venetian blinds and the Venetian blinds are of medium type, you find that the shading coefficient reduces to 0.64, and if you are using light Venetian blinds, then the shading coefficient becomes 0.55. If you are using roller shades and dark roller shades, shading coefficient is 0.59. If it is light roller shade, it is 0.25. This is for the single glass. Similarly for different types of glass, for example if you are using a double glass, a regular double glass of 3 mm thickness, you find that without internal shading the shading coefficient is 0.9, whereas for the single glass it is 1, and with the internal shading these are the values, right. Other types of glasses are, you can also have heat absorbing glass of 6 mm thickness. You find that for heat absorbing glass for 6 mm thickness, the shading coefficient without internal shading is 0.7, that means 30% less compared to a regular glass. Okay. So that is how, if you have this kind of information, then you can select the proper shading coefficient value from these tables, and once you know the shading coefficient value, you can calculate what is the heat transmitted into the building through this glass. Okay. Now, heat transferred through the glass due to solar radiation can be reduced considerably using suitable internal shadings. Okay, you might have noticed that when you are using internal shadings, the shading coefficient is less than 1. Okay, that means amount of heat transmitted is less than 1. Okay, so with this we know, everybody knows that if you want to reduce the radiation, you can simply put a curtain, or you can simply use a Venetian blinds. Okay, so thereby you can cut down the amount of radiation entering into the building. Okay, so that is good as far as the cooling load is concerned. Of course, there is a negative aspect to this. When you are using a dark curtain or Venetian blinds, etc., the light that is entering into the building also gets reduced. Okay, if light is not sufficient, then you may have to use some artificial lighting, right? So you have to pay for the artificial lighting. So again, you have to see the balance. You have to balance between the requirement for the light and requirement for, or requirement for reduction in the cooling load. Okay. And from the type of the sunlit glass, its location and orientation, and the type of internal shading, one can calculate the maximum heat transfer rate due to solar radiation. Let me give a small example. This is a very simple example. We have to calculate the maximum heat transfer rate through a 1.5 meter square area, unshaded, regular double glass facing south during June and December, without and with internal shading. Okay. The internal shading is light Venetian blinds, and the location is 32 degrees north, right. So the data given is, we have to calculate during June and December. Okay. So first let us do the calculation for June. For the month of June, the SHGF max from table is 190 watt per meter square. Okay. So this is the solar heat gain factor for the standard glass. Okay. Then using the values of shading coefficient from the table, that heat transfer rate is given by, this is the expression, Q is A into SHGF max into shading coefficient. If you are not using any shading coefficient, any internal shading, sorry, then you find that area is 1.5 meter square and SHGF max is 190 watt per meter square, and shading coefficient for the double glass is 0.9 from the table. So you find that QSG is 256.5 watt on June. Okay. And with internal shading, that means if you are using a Venetian blinds, then for the same date, right, you find that the maximum energy transmitted is again given by the same formula, area is same, SHGF max is also same, but the shading coefficient is different now, it is 0.51. Okay. So you find that the total or the rate at which energy is being transmitted, the maximum transmission rate is given by 145.35 watt. So from these you can see that with Venetian blinds you can reduce the energy transmitted considerably. It is almost 50% compared to without internal shading. And if you do the same thing for December, okay, so you find that the SHGF max for December is 795 watt per meter square. So without internal shading, QSG is 1073.25 watts. With internal shading, this is 608.175 watt. Okay. Again you can see here that because this is a south facing glass, the energy transmitted during summer is much less, whereas it is much higher during winter. Of course, obviously during winter you should not use any internal shading because you want this, whereas during summer you should use internal shading because you do not want this. Okay. Now let us look at effect of external shading. So far we have been assuming that the window is not shaded externally, that means the full area of the window is exposed to radiation. Okay. but most of the times we find that most of the windows will have some kind of an external shading. Okay, for example, an overhang, right? This overhang provides external shading. That means not all the area of the window will be exposed to solar radiation. Part of it is exposed and part of it will be in shade. Okay, so this will have a bearing on the heat transfer to the building. Okay, so let us see what is the effect of this. The solar radiation incident on a glazed window can be reduced considerably by using external shadings, for example, overhangs. Of course, the external shading can also be provided by, let us say, a tree or an adjacent building, right. So, but here I am assuming that it is based on the overhangs. Okay. So, by proper design of the overhangs, it is possible to block the solar radiation during summer and allow it into the building during winter. Okay. Thereby you can reduce the cooling load and also the heating load. So, what is the effect of overhangs? As we know that overhangs reduce the area of the window exposed to solar radiation and thereby reduce the heat transmission into the building due to direct radiation. Okay. Let me show this. So, this is the window. Okay. So, window has the dimensions of height h and width w. So, area of the window is given by h into w, right, and area exposed to solar radiation is equal to this without overhang. Okay, because the entire area is exposed to solar radiation. But if I am using an overhang with inset, let us say I am using an overhang with inset, this is the overhang with inset, the red hatched portion. So, you have the certain length of it, certain it has certain width and it has certain depth. Okay, depth of the inset is this, okay, and width is this, right. So, if you are using an overhang, you find that this hatched area at this particular incident, when the sun is at this particular position, this area is not exposed to direct radiation. That means this is in shade. Okay, only this much area is exposed to solar radiation. Okay, that means without overhang, the entire area is exposed to direct radiation, whereas with overhang, only the small portion is exposed to direct radiation, and this small portion is given here as multiplication of x into y. Okay, and at any point you can calculate x and y because this is related to your solar geometry. For example, this is related to your altitude angle beta, and it is also related to your surface azimuth angle. Surface solar azimuth angle alpha. Okay, what is the relation? You can find that at any point x is given by this relation, x is equal to w minus d into tan alpha, whereas y is equal to h minus d into tan beta by cos alpha. As I said, beta is your altitude angle, alpha is your wall solar azimuth angle, whereas w is the width of the window, which is equal to the width of the overhang, and d is the depth of the inset. That means this this dimension. Okay. So, if you know the dimensions of the overhang, what is the width of it, what is the depth of the inset, and if you want to find out at any particular incident how much area of the window is shaded, how much area of the window is exposed, then you can calculate it very easily if you can calculate the altitude and wall solar azimuth angles. Okay. Let me give a small example here. We have to calculate the energy transmitted into a building at 3 p.m. Okay, on July 21st due to solar radiation through a southwest facing window made of regular single glass. Okay, that means it is made of the reference glass. The dimensions of the window are height is 2 meters and width is 1.5 meters, and the depth of the inset D is 0.3 meters. Okay, now from the given data, that means at 3 p.m. That means our angle is 45 degrees. July 21st, you can calculate what is the declination on July 21st, and it is facing southwest. So, your zeta is 45 degrees. Okay. So, from the hour angle, zeta and declination, you can calculate the altitude angle, and if you do the calculation, you will find that the altitude angle works out to be 48.23 degrees. Okay. Similarly, you can also calculate the surface solar azimuth angle, which works out to be 39.8 degrees. So, this is the first step, you have to calculate these angles. Once you calculate these angles, you can calculate the dimensions x and y. Okay. X and y is the length and height of the unexposed area. I am sorry, of the exposed area, right. So, x is given as w minus d into tan alpha, where w is the width of the window, which is given as 1.5 meter, okay, and d is the depth of the insert, that is given as 0.3. Okay. So, you find that x is equal to 1.249 meters, and y is equal to h minus d into tan beta by cos alpha, where h is 2 meters, d is 0.3, tan beta is 48.23, and alpha is 39.487. So, if you substitute these values, you find that y is equal to 1.562. Okay. So, now you can calculate what is the transmitted energy because of solar radiation. So, that is now given by SHGF max multiplied by the shading coefficient multiplied by the exposed area. Okay. So, exposed area is x into y. So, that is given by 1.249 into 1.562, okay, this multiplied by this, and SHGF max from your ASHRAE table works out to be 230 watt per meter square, okay, because this is at 32 degree north latitude, okay, and the shading coefficient is 1, because this is a standard glass. So, you find that the radiation transmitted is 448.7 watts. Okay. If you do not use the overhang, you will find that the energy transmitted is W into H into SHGF max, that is 690 watts. Okay. So, you can see that with the overhang it is about 449, with without overhang it is 690. So, there is a considerable reduction in the energy transmitted to the into the building because of the absence of overhang. Okay. So, overhang is beneficial, right. Now, complete shading of the window in summer and complete unshading in winter is possible using separation between the top of the window and overhang. Okay. So, ideally we would like to completely shade it in summer, because we do not want any heat in summer, whereas we want lot of heat in winter. So, you want complete unshading. Okay. So, complete shading and unshading is possible using what is known as a separation. Separation is nothing but the distance between the top of the window and the overhang, and an infinite combinations of overhang width and separation dimensions can provide complete shading in summer and complete unshading in winter. Okay. So, let me show this. Okay. One thing I would like to mention here is that the position of the sun will be varying continuously. Okay. So, when I am saying that this overhang can completely shade this window, it can only completely shade at a particular point. Okay. It cannot completely shade all the time, right, because the position of the sun varies continuously. So, normally what you have to do is you have to find out the point at which the load is likely to be peak, okay, and the design overhang in such a way that during summer the window is completely shaded at this particular instant, okay, and during winter it is completely unshaded. So, this is one thing you must remember. Again, all these dimensions and all will be varying between latitude to latitude, because the solar geometry is varying from latitude to latitude, and it also varies from the orientation to orientation. Okay. So, these things again you have to keep in mind. Now, you can see from this figure that suppose you have this dimension W naught, and this is what is known as separation. Okay. So, this is your window. If you provide this separation and this much width of the overhang, because this is your overhang, right, you can completely shade this window, because the sunlight is falling at this point. So, the entire portion, this entire thing is in shade, okay, whereas the whatever is below this is unshaded. So, no solar radiation is entering into the indoors which are on this side, right. If you take this W naught and this S, you can also take for example this W naught, okay, and this S, then also you can completely shade the window, or you can take this W naught and this S, okay, again you can completely shade the window. That means a large number of combinations of W naught and S are possible, which can result in the complete shading or unshading of the window. Okay. Of course, there are certain limitations of fixed overhang. So far we have been discussing about fixed overhang. They have certain limitations. What are the limitations? Any overhang provides protection against direct solar radiation only. Okay, it cannot provide any protection against diffuse or reflected radiation, and you find that because of the variation of the transmittivity with incident angle during the peak summer time, you find that for a vertical surface only about 40% of the total solar radiation consists of the contribution of direct radiation. Okay, that means about 40% of the total during summer is because of the direct solar radiation, and provision of overhang can only reduce this, right. That means it can only handle the 40%, rest 60% cannot be handled by the overhang, because the rest 60% consists of diffuse as well as reflected radiation, and a overhang cannot reduce diffuse and reflected radiations. Okay, external shading, right. And you find that sometimes overhang can work in a negative manner. For example, the overhang may actually reflect the ground radiation onto the windows, right. So it is a bit it may look like a paradox that you provide an overhang, you find that there is more heat in the room. Okay, this happens because if your ground is highly reflective, right, then first the radiation will be reflected from the ground onto the overhang, and from the overhang onto the wall, onto the window, right. So ultimately, because of these reflections, you will find that there is a lot of radiation entering into the building, not through direct radiation but through reflected radiation. Okay, then overhang is working in a negative manner. Okay, so this is one of the limitations of the fixed overhang. And during mornings and evenings, when the sun is so low in the sky, that overhangs can provide only minimum protection. Okay, so they are not really very useful during mornings and evenings. And overhangs are truly effective for windows facing 30 to 45 degrees of south. Okay, so overhangs are not very useful on east and west direction, for example. Why? Because during on east and west direction, the maximum radiation occurs during morning for east and during evening for west, and during morning for east and during evening for west, the position of the sun is very low, right. When the position is of the sun is very low, that means the altitude angle is very low, the overhang cannot block the direct radiation. Okay, so it is not of no use. The only way of blocking solar radiation on east and west faces during morning and evening is to use something else like a wall or a tree or an adjacent building, right, but not overhang. This is the another limitation of overhang, right. In spite of all these limitations, overhangs are very widely used because they also provide protection against rain. Okay, so overhangs are highly recommended. Okay, so this is as far as the effect of solar radiation and how to calculate the cooling and heating loads. This requires a little bit of extension, but how to calculate the energy transmitted into the building due to solar radiation, first through opaque surfaces and next through transparent surfaces. Again, for the transparent surfaces with and without external shading. Okay, so from the discussion we can calculate all these things. Now let us look at another aspect of cooling and heating load calculation, that is ventilation and infiltration. Air inside a space should be pure to ensure healthy and comfortable living conditions. However, conditioned air normally consists of several pollutants. Okay, what are these pollutants? These pollutants are odors, various gases such as carbon dioxide and volatile organic compounds or VOCs, and particulate matter. Okay, so you find that any conditioned space will not be 100% pure, but it will consist of these impurities. And if these impurities, if the concentration of these impurities goes beyond a certain level, you find that the indoor environment is not neither it is healthy nor it is comfortable for the occupants. Okay, so these pollutants are due to both internal as well as external sources. Internal sources are human beings, appliances, etc., whereas the external sources are the outside air itself. And indoor air quality, the abbreviation is IAQ, can be controlled by the removal of the contaminants in the air or by diluting the air. That means you can maintain the purity of the air inside a conditioned space either by removing the contaminants or by diluting the air. Okay, there are you can use both of these techniques. Now, with reference to this indoor air quality, what is ventilation and what is the purpose of ventilation? The purpose of ventilation is to dilute the air inside the conditioned space, okay, thereby maintain required indoor air quality. And ventilation is defined as the supply of fresh air to the conditioned space either by natural or by mechanical means for the purpose of maintaining acceptable indoor air quality. Okay, so the whole purpose of ventilation is to maintain required indoor air quality, which is very much essential for comfortable and healthy living conditions, and this consists of supplying fresh air, and either by natural means, that means either by natural ventilation, or by mechanical means, that means either by using an exhaust fans or blowers, etc. Okay, this is the definition of ventilation. And ventilation air generally comprises of fresh outdoor air and some amount of recirculated air that is treated to maintain acceptable indoor air quality. Okay, so the ventilation air need not be all outdoor air, it can be a part of outdoor air, and some part of it can be recirculated. When you are using recirculated air for ventilation purpose, you have to treat it first, then use it for ventilation. Okay. And if the outdoor air is not pure, that means outdoor air itself is dirty, it consists of a lot of dust, then it also has got to be treated before supplying to the space. Though the amount of fresh air required for breathing is quite small, that means its amount of fresh air required is about 0.2 liter per second per person. From breathing point of view, the actual requirement of fresh air is large, as ventilation air, in addition to providing oxygen for breathing, also has to serve the following purposes. Okay, so only one of the purpose of ventilation is to provide oxygen. In addition to providing oxygen, ventilation air also has to dilute the odors inside the occupied space. This is very important to a socially acceptable level. Okay, so odor dilution is an important function of ventilation. Second important function is to maintain the carbon dioxide concentration at a satisfactory level. And the third practical requirement is that it should be able to pressurize the escape routes in the event of fire. Okay, so these are the other important functions of ventilation air. Let us look at the estimation of minimum outdoor air required for ventilation. How do we find how much air is required for ventilation? From energy conservation of point of view, it is important to choose the ventilation requirement suitably, as ventilation is one of the major components of system loads. Okay, so it is very important to choose it properly. You can't have lot of ventilated air, then you will have to pay in terms of running cost. The amount of air required for ventilation purposes depends on several factors such as application, activity level, extent of cigarette smoking, etc. So several factors affect the amount of required air. Okay, and based on several studies extending over several years, guidelines for minimum ventilation requirements have been established. For example, one of the guidelines is ASHRAE standard 62/1989. Let me give a small example of this ASHRAE standard. What does it say? This is a typical outdoor air requirements for ventilation adapted from ASHRAE standards. You can see that for offices, if the occupancy level is 7 people for 100 meter square floor area, and if it is a smoking zone, you require 10 liter per second per person. Okay, and if it is a non-smoking zone, you require 2.5 liter per second per person. Okay, and for operation theatres, you require high levels of ventilation, and the occupancy will be 20 persons per 100 meter square. And normally smoking is not allowed, but still you require high ventilation air because you have to maintain high level of purity. And for lobbies, where the occupancy is slightly higher, 30 persons per 100 meter square floor area, and if smoking is allowed, you require about 7.5 liter per second per person, and if smoking is not there, then 2.5 liter per second. And for classrooms, for example, where the occupancy is still higher, 100 persons per 50 persons per 100 meter square floor area, and normally smoking is not allowed, and the required ventilation is 8 liter per second per person. Okay, and for meeting places, these are the values. So one thing you can notice here is that as the occupancy level increases, the required amount of outdoor air increases. Similarly, if you are allowing smoking, then outdoor air also requirement also increases. Okay. So based on, if you have this kind of data, you can decide what is the outdoor air requirement. Let us see how to estimate infiltration. Now so far I have been discussing about ventilation, and let us see what is infiltration and how to estimate infiltration loads. First of all, infiltration, it is defined as the uncontrolled entry of untreated outdoor air directly into the conditioned space. Okay, so you have to carefully note the difference between infiltration and ventilation. Both involve supply of outdoor air, whereas ventilated air is supplied in a controlled manner. Infiltration is uncontrolled entry. Okay, so you have no control on that. And infiltration of outdoor air takes place because of two effects. One is what is known as wind effect and the other one is what is known as stack effect. As the name implies, the wind effect means infiltration due to the wind blowing over the building. So, whenever wind blows over the building, pressure differences are created. Because of these pressure differences, outside air enters into the building and the air from the building leaves the building. Okay. This is what is known as wind effect, and the second effect is what is known as stack effect. This is nothing but the entry of outdoor air because of the buoyancy effect. So, the buoyancy effect is created because of the temperature difference between the inside and outside. Whether it is summer or winter, the inside temperature will be different from the outside temperature. You have some temperature difference. So, because of this temperature difference, there will be some density differences between the outside air and inside air. And if your building has some openings, because of the density differences, there will be entry of outdoor air into the building and some amount of or the same amount of air leaves the building. Okay, so this is what is known as stack effect. In commercial buildings, even though infiltration supplies outdoor air, in commercial buildings efforts are made to minimize infiltration because it is uncontrolled and unreliable. So, you cannot make any design depending upon infiltration because it depends upon unreliable factors such as wind and stack. Okay, so generally it is reduced. And so, what are the measures to reduce this? These measures, as you know very well, are the use of vestibules or revolving doors, use of air curtains, building pressurization. If you pressurize the building and if the inside pressure is higher than the outside pressure, no outdoor air can enter. So, thereby you can reduce infiltration, and you can also use proper sealing of doors, windows, etc. Thereby you can reduce the infiltration loads. Now, the estimation of the exact amount of infiltration is very difficult as it depends on several factors such as the type and age of the building, indoor and outdoor air conditions, outside wind velocity and direction, etc. Okay, so analytical estimation is very difficult. There are several methods are used. One method is what is known as air changes per hour. In this method, depending upon the building type, whether it is a loose building, medium building or tight building, infiltration rates are specified or related empirically to wind velocity and temperature difference. So, if you know the wind velocity and temperature difference, using the empirical equations you can calculate the infiltration rates. And data is also available for infiltration rate through different types of windows, doors, etc. Okay, now let us look at heating and cooling loads due to ventilation and infiltration. Due to ventilation and infiltration, buildings gain sensible and latent energy in summer and lose sensible and latent energy in winter. So, you have to note here that the energy transfer is both in the form of sensible as well as latent modes. Okay, and the energy is gained in summer and it is lost in winter, and the sensible and latent heat transfer rates are simply given by Q sensible is m dot Cp into delta T, which is we can write in terms of volumetric flow rate, that is V naught into density into Cp, and latent heat transfer rate, that is this. Okay, here HFG is the latent heat of vaporization, m dot O is the air flow rate due to infiltration or ventilation, and WO and WI are outside moisture content and inside moisture content, and T naught and Ti are the outside dry bulb temperature and inside dry bulb temperature. And as I have written here, m dot and V naught are mass and volumetric flow rates due to infiltration and ventilation. So, if you know the infiltration ventilation rates and outdoor and indoor condition, you can calculate what is the sensible heat transfer because of ventilation and infiltration, what is the latent heat transfer rate because of infiltration and ventilation. Okay. So, that is how you can calculate, but one of the major difficulties is to find out the infiltration rates. Okay. At this point I stop this lecture and we will continue this discussion in the next lecture. Thank you.